Whole discontinuity. Let's talk about whole discontinuity. Let me do some examples for whole discontinuity. So the very first example is example number 1. If I have a function f of x, it is a piecewise function with the two pieces, x under the root and 0. For the x under the root, x must be greater than 0. For 0, for the second piece, x must be less than 0. It is a piecewise function with the two pieces, 1 and 2. Let me draw their graph in xy plane. For the first piece of the function, which is x under the root, my graph will be in this shape, which extends on the right side. This is the typical graph for x under the root. According to this location point, x must be greater than 0, which means that my function must be greater than 0 in the first quadrant on the right side, not less than 0 in the second quadrant. X is greater than 0. So it's going to start from the origin and will go greater than 0 in the first quadrant. But since there is no equality sign here, x is not equal to 0. So 0 has not been included. Therefore, I have empty circle at the origin. 0 has not been included. The function is undefined here exactly at 0. It is an empty circle. It is a free space. 0 is my origin. The graph for the second piece, which is 0, is this. It extends on the left side. This straight line is my 0. But look, x is less than 0 here, which means that I'm gonna come lesser than 0 in negative direction. Negative 1, negative 2, negative 3, up to infinity. X is less than 0. Again, there is no equality bar here. Therefore, its end is an empty circle. Exactly on x equals to 0, the function is undefined. There is a discontinuity here, which is a whole discontinuity. First piece is greater than 0, second piece is less than 0. But both the pieces have no equality bar, so 0 has not been included for both the pieces. They are disconnected here. If you compare this 0 with the previous example, there is a difference. Last time I had 0, which was only a fill-in circle, because look, it is according to this location point where x only equals to negative 2, not less than or greater than. Therefore, I had only fill-in circle here. Since it is a constant, if x is less than negative 2, I'm going to draw a straight line here, not a fill-in circle. Straight line lesser than negative 2 in the negative direction. If x is greater than negative 2, I'm going to draw a straight line on the right side greater than negative 2. But since x only equals to negative 2 here, therefore I'm going to put only fill-in circle here at this point. I shouldn't draw a straight line here. Here for this 0, x is less than 0. So I'm going to draw a straight line lesser than 0. X is not equal to 0, less than 0. Now again you will be confused that why I put an arrowhead here and arrowhead here, because look, I have only one border value on the right side here. I don't have the second border value here. So on the other side, the function is banging in infinity. The function is not limited on the other side. Only one side has been mentioned, which is 0 here, and also 0 for this function. X is greater than 0, but it doesn't mention the other end, that where it ends. I have nothing on the left side, therefore greater than 0 means that it will start from here and will go in infinity in the right side. Similarly, x is less than 0 means it will start from here and will go in negative infinity on the left side. Now let me first check this whole discontinuity. It is going to be a mathematical and graphical work, that whether the regular limit equals to the actual value or not. So my left hand side limit is limit of f of x where x approaches 0 from the left side. And when I started approaching from the left side, I was getting closer and closer and closer up to the point which is very, very near to 0, like negative 0.000001, which approximately equals to 0, but not exactly 0. So approximately at x equals to 0, my left hand side limit is 0. It is 0 here. For the left hand side limit, I'm approaching 0 here because look, my exact value is 0 here. I was getting closer and closer and closer up to the point which is extremely closer to 0, like negative 0.00001. So approximately at x equals to 0, this piece of the graph makes the point 0 along y-axis. it is on 0 along y-axis. It is an origin. Therefore, the left-hand side limit equals to 0. But what about the right-hand side limit? My right-hand side limit is limit of f of x, where x approaches 0, but from the right side. I was getting closer and closer and closer up to the point which is very close to 0, like positive 0.000001, which approximately equals to 0. So approximately at x equals to 0, my second piece of the graph makes the point 0 along y-axis. Look, my exact value is 0. I'm approaching 0 here. I have nothing to do with the other end of the graph. I'm only dealing with this end of the graph because look, my exact value is 0. So when I started approaching from the left side, I was getting closer and closer and closer up to the point which is extremely closer to 0. So approximately at x equals to 0, this piece of the graph joins the y-axis at 0. Similarly, when I started approaching from the right side, I was getting closer and closer and closer up to the point which is extremely closer to 0. Therefore, this piece of the graph makes the point 0 along y-axis. Since my left-hand side limit is 0 and my right-hand side limit is 0, therefore left-hand side limit equals to the right-hand side limit. So my regular limit, which is limit of f of x, equals to 0. My regular limit exists here because left-hand side equals to the right-hand side. My left-hand side is 0, my right-hand side is 0, so my regular limit is also 0. But what about the actual value? My actual value, which is f of 0 at x equals to 0, my function is undefined here. Why? Because it is an empty circle. It is a free space. These two pieces are disconnected here at the origin. They are not connected with each other. There is an empty circle. It is an empty space. For the actual value, you have to put x equals to your exact value. My exact value is 0 here. At x equals to 0 means that exactly on x equals to 0 at the origin, at this point, the function is undefined. It is not defined here. There is a discontinuity. Therefore, my actual value is undefined. It is not defined here. It is not a fill-in circle. It is an empty circle. So it's gonna be undefined here. Since my regular limit is not equal to the actual value, my regular limit is 0. My actual value is not even defined, so they are not equal to each other. Therefore, at x equals to 0, the function is discontinuous at x equals to 0. At this point, I have a discontinuity. But what kind of discontinuity? A whole discontinuity. We have discussed last time that whole discontinuity is a removable discontinuity. So I can remove this discontinuity from here. Let me remove the empty circle with the fill-in circle here. What does that mean? It means that I'm going to add the third piece of the graph here, which is a fill-in circle. So my new piecewise function will be f of x equals to x under the root 0 and 0. Remember last time I had only x under the root and 0. But there was an empty circle here, which was a whole discontinuity. I can remove this whole discontinuity by a fill-in circle. When I add a fill-in circle here, it means that I'm going to add the third term here, which means that I'm going to add the third piece of the graph, which is 0. When I add one more piece, which is 0, at x equals to 0 here, at x equals to 0 means that I'm going to put fill-in circle here. X equals to 0 means that x has been included. X not less than 0, not greater than 0, equals to 0, which means that I'm going to put fill-in circle here exactly on x equals to 0. I had a discontinuity here. Now the function is a continuous function from here up to there. It is a continuous function. These two pieces are connected with each other at this point because of this fill-in circle by adding one more piece of the function. Therefore, my actual value f of 0 will be 0. It happened only by adding the third term, which is 0. Exactly on x equals to 0, I have a fill-in circle. At x equals to 0, my function is defined, which is 0 here. Since my regular limit equals to the actual value, which is according to this equation, limit of f of x where x approaches c equals to f of c. The limit of f of x where x approaches c is my regular limit, which is 0, equals to f of c. F of c is my actual value, which is also 0. Regular limit is 0. Actual value is 0. Since left hand side equals to the right hand side, Therefore, the function is continuous at 0. Now the function is continuous at x equals to 0 here. Last time I had discontinuity here, but then I removed this whole discontinuity, and now the function is continuous here.